Now, here's another piece of evidence, and this is a little trickier to understand. But when they started measuring the magnetic field, now you might wonder, oh, why would they have to measure the magnetic field? Well, it turns out when you're having things like nuclear submarines in the ocean, you got to understand exactly where you're at using compasses, but compasses would be thrown off by the magnetic field that's embedded in the ocean floor. If you have iron-rich minerals in the ocean floor, then that's going to create these little magnets. So check this out. What happens then is the magnetic field of the Earth, if a mineral gurgles to the surface in a lava form, any iron-rich minerals in there are going to orient north and south along with the way that the magnetic field is on Earth. Well, it turns out that Earth's magnetic field sometimes will switch. It will reverse. Okay? So what they end up finding off the coast of Iceland around the mid-Atlantic ridge is these parallel magnetic stripes of reversed polarity on either side. Please write this down. And what's happening is that on either side, you have these symmetrical stripes. And at first they were like, what's going on with that? That pattern can't be coincidental. Well, let me show you what caused the kind of the striping and stuff, okay? Okay, now the Earth, as you may or may not know, has a magnetic field, right? And so here's a magnet. And so kind of like there's magnetic field, there you go. And just to kind of show you something interesting about this with the magnetic field, you can kind of see the shape of it by sprinkling iron filings around that magnet. And you can see how the lines of force sort of start to shape up there. And they form this magnetic field around that magnet. Well, the Earth has the same kind of thing going on with that. It's generated by the rotation of the solid iron ball and round with the liquid iron around it. What's going on inside the Earth's core. So this magnetic field then will influence a compass, right? So a compass needle will line up in orientation with the magnetic field. Okay? Now the Earth's magnetic field, you probably know what a compass does. Whoops. Okay. So anyway, here we are. The compass always points north-south, right? It's a magnet lining up with Earth's magnetic field. And in this case, north is that way, right? Now, I'm going to put this magnet and say, okay, here's the magnet. Okay. Here's the magnet with a magnetic field that's oriented north and south. Now, what happens with the Earth, strangely enough, and this isn't fully understood, but every 100,000 years or so, the Earth's magnetic field actually flips. It rotates. And when it does, the magnets would face in the opposite direction. Now, imagine you have, imagine you have a, like lava coming out at some place like underneath the water or whatever, and the lava solidifies. Any iron and magnetized elements in there or minerals in there are going to orient to the Earth's magnetic field. Okay, so if some come out, they're oriented this way, and then 100,000 years later, there's magnetic field flips. Well, there you go. It will orient that way. And so you can tell when you look at the magnetic field in those minerals embedded in the rocks, you can tell which way the Earth's magnetic field was oriented. North-south, the way we know it, or south-north, which is the opposite of the way we know it now. The way we know it now, we call it normal because that's what it happens to be. But it's just as often reversed from what we see. Okay, so the magnetic field reverses, and that's recorded in the rocks. All right, so you have these parallel magnetic stripes that they've found recorded in the ocean floor. Well, if you notice, there's symmetry there. For every stripe on one side, there's an equal stripe on the other side. There's a pattern that repeats. And at first they were like, what's going on with that? Well, when the Earth's magnetic field reverses, that gets recorded in the rocks, like I was just saying. So go ahead and write this down. The magnetic reversals are recorded in the rocks. And here what we have is there's a number of these reversals that have been recorded. They happen about every 100,000 years or so, maybe a little bit less than that. But it can vary quite a bit. But if you have these molten materials with those iron-rich minerals in there, they will orient and record that magnetic field. And a magnetometer, a device that can be dragged behind a ship, will record that magnetic field. And so what happens then is they can record the magnetic field that's recorded at a given time when the Earth, when the lava comes to the surface, and then as it moves outward on either side, those reversals will be recorded in those magnetic stripes. So again, it's that outward movement is what's being recorded with these parallel stripes. And that outward movement is seafloor spreading. That's how they realize, wait a second, it looks like the Atlantic Ocean is getting wider and wider and wider. That means that North America and Europe are getting further and further apart, and South America and Africa are getting further and further apart. What the heck? It turns out that Alfred Wegener was right. The Pangaea continent was once together, but as the seafloor spreads out, the continents are actually drifting away from each other. So this is the evidence that verified that Wegener was right. That if way back in the olden days, you had the very narrow Atlantic Ocean, and as new ocean floor would be made in the middle at the mid-Atlantic ridge, it would record that normal magnetism. And as it spreads out, and then it reverses, now it would record a reversed magnetism. You see what I'm saying? And so those stripes show that the Atlantic Ocean is actually spreading out, seafloor spreading, is spreading out from that mid-Atlantic ridge. Now here's the real clincher. Radiometric dating, what that means is you can take the rocks and measure how much of different kinds of radioactive isotopes and can tell how old they are. Well, take a look at this. 0 to 2 million years, that's the youngest rock, and it's right on the ridge. And the further away you go from the ridge, the older it gets, right? And it's the same as it goes off on either side. And same here, we're going to be taking a look at this one here when we get to the Pacific Basin. But right now we're just talking about the Atlantic with the seafloor spreading. So it turns out Wegener was right that what we have here with the discovery of this mid-Atlantic ridge after World War II is the continents are drifting apart. Okay? So here's the concept. He thought, man, how the heck could the continents just be plowing through the ocean floor? Turns out they're not. It turns out there's new ocean floor being made, and the force that's driving it. He had no idea what force was driving it. Well, now, this isn't fully understood, but there's a theoretical explanation for what's driving the force. Okay? As the slabs move apart, the seafloor spreading happening out. Oh, by the way, write down seafloor spreading. I don't know. This one took me by surprise. But that's the idea. It's spreading out from the middle, and it's driven by convection in the mantle. Convection. That's the vocabulary word. Write this down. What's happening is you got the outer core here, and then the mantle, which has basically lava, or it's called magma when it's underground. And as it rises to the surface, it creates new seafloor, and it spreads out away from each other on either side, and that spreads it out, okay? Convection in the mantle. What's convection? Well, that's what's coming up next. Convection, you might remember if you learned about this last year studying weather, you might learn that hot air rises because it's less dense. Well, it turns out that hot magma that rises is less dense, and you get these convection cells going. So here's a couple demonstrations about those, okay?